Today I want to touch on the commission report in the context of the themes of the meeting that you're hosting. Talk about justified trust in both engineering and performance, touch on a couple of issues there, directions. Focus on augmenting human capabilities with AI systems, and then end with a reflection about mastering mix of initiatives where humans and AI systems each take initiative in a volley. First, on the National Security Commission on AI, it was established as an independent commission a couple of years ago, and the charge from Congress was the commission should consider methods and means necessary to advance the development of AI, machine learning, and associated technologies to comprehensively address the national security and defense needs of the United States, with its recommendations going to Congress and the president. And their final report, which is almost 750 pages long, I think all interesting pages, but I'm going to try to focus down this audience, what I think is most important for the topics of this meeting. The final report is 16 chapters. I'm going to focus today, and I refer people to nscai.gov to read this work. Chapter 7 on establishing justified confidence in AI systems, as well as background on responsible and trustworthy AI in the appendix called Key Considerations for the Responsible Development and Fielding of AI. Chapter 11 will also be of use and interest to this group on accelerating AI innovations. Now, on that topic, as commissioners, we spent quite a bit of time discussing and debating key directions for AI R&D. Now, one of the key opportunity areas, getting back to today's meeting, is in the area of human AI interaction and teaming. And details of this can be found in the chapter 11 of the report. But on that topic of R&D priorities on human AI teaming moving forward, the report called out key directions with human AI complementarity, methods for augmenting human reasoning, mastering fluid handoffs in mixed initiative systems, and technologies more generally arising and being focused on perceiving and understanding human intention, communications, including spoken, speech, and written gestures. On establishing justified confidence in a focused deep dive in a line of effort that I chaired, we call out in the report that AI systems must be developed and fielded with justified confidence. And the comment that if AI systems do not work as designed or are unpredictable in ways that can have significant negative consequences, leaders will not adopt them, operators will not use them, Congress will not fund them, and the American people will not support them. And in that justified confidence chapter, we call out 5 areas that really require deep investment: robust and reliable AI, especially when it comes to new approaches on the adversarial side, adversarial machine learning, for example. Really investing in testing, evaluation, verification, and validation of these systems, calling out NIST to play a critical role. Leadership on having the right people in place at agencies to understand the technology and help to guide it. Accountability and governance to make sure things go well in terms of development, fielding, and integration. And on human AI teaming and interaction, really calling out sustained multidisciplinary initiative through investments in DARPA, ONR, national security labs across the nation. I wanted to just touch on 2 critical foundations that are mentioned in the report that I think are important in trust of AI systems. One is in the engineering of AI systems, and one direction we focused on in the NSCAI report was really requiring key schemas to document key aspects of each of what have been called out as critical phases of the machine learning life cycle. For example, documentation of data. There's been interesting work over the last several years on, for example, the data sheets for data sets, on looking at detail to characterize where data came from, its provenance, its purity or error characterization, and so on. But we need efforts to extend documentation to all phases, and work like the About ML effort at the Partnership on AI, which is an industry and civil society nonprofit AI research consortium are looking at what are some standards across the community that would apply to government, non-government, civil society agencies for documenting and staying in touch with and tracking over time each component and the intention and details about assumptions, for example, made in building those components. Another area is in the performance space. And just as an example of a direction here and of course, we need to have trust in the real-world execution of systems, and we need to characterize their performance on representative and realistic test sets. But a key problem to date is that testing and reporting is done with aggregate measures. People feel good when they see 82% accuracy. But unfortunately, real-world actions don't come in aggregate. We care about specific situations. So these aggregate metrics can hide important conditions of failure where the model may be underperforming either for a particular input condition or for some population groups. And they give the impression that model accuracy is uniform when we know that in the real world it is not. So discovering pockets of data with high error is a tedious and time-consuming process. It requires streamlined infrastructure for error detection, which engineers and developers might not have. So work on my team at Microsoft has pursued, and we've open sourced these methods, tools for going through and identifying pockets of cluster and displaying them to end users in with different controls to see where the system does really well and where the aggregate would hide critical failures that you would not see with the summary statistics, even in tree form, for example, in a sense where the errors line up according to different states of the world as defined by key branching features. This tool is called the Error Analysis Tool. It can easily be found on GitHub. Now, in real-time use, key aspects of trust include generating insight, building rationale or explanations on core contributing factors to recommendation. So we need explainable methods that are highly accurate to describe, for example, contributions to a probability, for example, of an outcome or recommendation or prediction. We also need case-specific guidance. Going back to that error analysis tool, it's not just for engineering, it's for real-time use. So imagine there's an identify friend or foe task type X, and the error analysis working on test sets has discovered that if the distance of object for object recognition is greater than 100 kilometers and lighting is dusk, there's a only 59% accuracy on that situation. Or if the IFF task distance at 100 kilometers, but there's direct sunlight glare, it's supposed to 42%. You would not see that without this kind of a study that goes into clustering these states. And these kinds of displays we're studying at Microsoft are very valuable, we believe, when it comes to real-time uses, to know you're in a pocket of error or a pocket of trust for that system. Another important set of directions, we need to think through multiple dimensions of facilities that can help with human AI collaboration and trust. We've done some factorizations of what I would call human needs for healthy and robust interaction with AI systems. We developed this on my team. They're referred to as guidelines for human AI interaction. They're now being used broadly across Microsoft and elsewhere, but you see these categories here. Guidelines for design, for example, initially make clear what this can do, make sure how well the system can do what it does. When wrong, for example, the yellow box, the gold boxes at the gold row here, supporting efficient invocation, supporting efficient dismissal of AI applications or features running in the background of a core technology or service. Support efficient corrections. Scope services when in doubt. When in doubt, you can use scope it so it's still useful even if it's less precise, and make clear why the system did what it did. And even over time, remembering what just happened. So a user can say, for example, do that again, or stop that, or explain that to me, that last action to me, and so on. There's a toolkit available for implementation with guidance on these guidelines on our website. Now, on another front, we have to consider with trust how human operators work with AI systems as they are updated over time. There have been newsworthy events about updates being introduced and how they can be costly in light of mental models that human operators might have of the last version or current version before it was updated of an AI system. For example, in 2018, Tesla released an update to fix a problem in the braking system of their cars. And it was an improvement, but if users were not aware of the change or they can't quite understand what has happened, it can be puzzling or mysterious or even dangerous. Same is true for the unfortunate and tragic 737 MAX. This headline in the New York Times captures it all. Jet software was updated, but the pilot's understanding of that software was not. So we've done quite a bit of work on trust and updates with AI systems that are being used over time. You can imagine a system being used, let's say, in a medical facility or in a defense application over time. There are many cases coming in, and the user generates a model, for example, of how well the system does on different patients, for example, and learn how well they can trust the advice from the system for its distribution of errors it makes. With a model update, you might have a new model, let's say predicting readmission of patients within 30 days of discharge. And the updated model went from an 80% accuracy to a 90% accuracy. But we've discovered it's very common when you do an update with refreshed data or extended data sets to see a shift of the distribution of errors. For example, from the errors in pink here, from all the young kids to maybe older folks. And we have a set of methods and approaches and representations for taking a baseline model, looking at the updated model in terms of, for example, its error distribution. And we call a system that has where all the previous errors have, are sort of, there's no new errors introduced, and we just have seen a decrease in the current errors, a fully compatible update versus a fully incompatible update where all the errors are new. They weren't there before, even in a model that's more accurate, or partially compatible update. And we have tools now also available on GitHub for doing a study over time of models and giving you a sense for new errors or regression, fixed errors, progress, for example. Now, with that, I want to move to a key opportunity area that I've been interested in for a long time on enabling more fundamental couplings of humans and AI systems at the level of human cognition, on the prospect of designing systems that understand human cognition and human cognitive limitations, that understand, for example, human blind spots and biases, and that work to complement human thinking explicitly with knowledge of the cognitive limitations of people. There's over 100 years of research in cognitive psychology in different dimensions, for example. It's captured by this high-level graphic in memory, attention, and judgment. Now, at Microsoft, over time, we've done studies along the lines of attention and memory and judgment in our augmented cognition research. For example, building models that can compute the cost of interrupting somebody on current task, or model of what someone will forget or remember over time, or a model of what humans would be surprised by. We call these surprise models. You can go to our website to look at the various pieces of work in this space, but I want to just do a couple of examples right now. For example, in judgment, just starting real basically, a recent study from Johns Hopkins estimated that over 250,000 deaths annually in the United States are caused by human errors, making these deaths the third leading cause of death, right after heart disease and cancer. Unfortunately, these deaths are now the fourth most common cause of death in the US, being displaced by COVID-19. But the high rate of death based in medical errors, human errors, frames a key role for AI systems, and that is of a safety net, analogous to the safety net pictured here for capturing accidental falls by workers during the construction of the Golden Gate Bridge. To err as human, we have to expect errors, but AI can help as a safety net. So as an example of a project in this space, there's a tragic phrase used in medicine called failure to rescue, which refers to death after a treatable complication that was missed. Failure to rescue, it really is a challenge in hospitals worldwide. And in work to address this challenge, we collected, this was a student, Day Lee, an advisee of mine at University of Washington, a large database of patients from the hospital system that came in healthy, that didn't leave the hospital. When I say healthy, came in for a optional medical procedure that they had agreed to do. Wasn't a life in that situation, and then ended up dying in the hospital. We basically built systems that over time can learn to stamp actions from the electronic health record, identify life-saving maneuvers, and then predict these the life-saving maneuver on the frontier in 4 hours, 8 hours, 12 hours ahead to address this issue of people missing, for example, major organ system failures over time. In the memory space, we've done quite a bit of work in this area. If people are using the industrial version of Exchange now on Azure, they'll be familiar with the idea of Cortana trying to come up with things you might forget, promises you've made in email to your colleagues, friends, and family. How often have people have had to be reminded of not sending a title and abstract shortly? I think Peter and I just had this issue. I was reminded by Cortana and Peter Friedland for this talk, as well as weekly updates and so on. Now, so far, we've looked at the design of systems that can sort of aim to assist people with major problems, but we haven't looked more formally into computational methods that can help with the weave. And I want to talk right now about joint models of cognition and the world. So a human operator looking at a system, let's say it's a complex diagnostic challenge, troubleshooting healthcare, has a probability distribution, let's assume, in their mind about what's going on. With joint models of cognition and the world, the goal is to build probabilistic models trained from data that can actually do an estimate of what that distribution is for the human with the level of training and experience that they might have. In the meantime, an AI system might have a broader, more focused, intensive model of a system, for example, a space shuttle propulsion system, and it has its own distribution of what it would do, what it thinks is going on in the world. And it can actually, with this joint model of cognition in the world, we bring the estimate of what the human knows together with what the system believes is a gold standard approach to handling a situation with the human operator in charge. And we think about what's the ideal advice to give to the end user, the operator responsible for taking action. Now, during my graduate work at Stanford, I sought to test out ideas on predictive models in real-world applications, and I actually, this work brought me to as a NASA graduate student fellow, based through a grant from Ames Research Center. I had a chance to go down to the Mission Control Center at Johnson Space Center to learn about how people worked, and one challenge that came up was people were very interested in one of the areas of mission control of diagnosing space shuttle propulsion system failures during launches and deorbit and reentry. And that took, of course, modeling the actual ground truth system and building Bayesian networks at the time to do diagnosis. But what we noticed was people actually are responsible for taking actions, and they need to get the right kind of advice under time pressure. And in reality, they're looking at large displays of sensors streaming data from the shuttle systems. This is actually someone working at Mission Control in those days, in the era that I was there. And what we discovered was we should be building models, not just at the base level, but models that include beliefs of the user and use that to drive prioritization of display in real time. As an example of how to prioritize which information should be looked at more carefully from the point of view of the system, using intensity of color as the alerting and triaging metaphor. Now we can think about deeper weaves for complementarity, and one deeper weave that we're exploring, or a type of deeper weave, is using machine learning and reasoning itself to help with the weave of human and machine capabilities. So here's an example of some work in this space, and it's a particularly exciting direction for me in that we're now thinking through really learning about the complementary talents of people and machines. So the frame for this work was a few years back. It was a challenge called the Chameleon Competition. It was held to build an AI system that could detect breast cancer metastases in sections of lymph node, a really critical review challenge when someone has had breast cancer or is recently diagnosed, understand whether the breast cancer has gone beyond its local site. Now, the best machine learning system in this competition, Chameleon, maybe to the happiness of human pathologists, was not as good as the best human pathologists. The humans had a 3.4% error rate, which captures their false positives and false negatives. Now, surprisingly, a simple combination of the AI, the best AI system, and the human output about cases brought the error down to 0.5%, which means that the AI system is bringing the human error, when properly fielded, down by an 85% reduction. Now, knowing this, we gained access to the raw data, including the human data from the Chameleon competition, and then thought about how can we use this data about where people do well versus not so well. And if you think about traditional machine learning, you have a big data set that's tagged with the outcomes. You have a test set. You basically train a system, and you minimize a loss function to build a neural network that performs ideally with the best set of weights through procedures like stochastic gradient descent. Now, given that we had a human performance data set now, we thought deeply about how can we actually build a new approach where we take the AI solo idea and at training time, give the system the ability to look at the value of human expertise on a case-by-case basis and actually compute the value of asking a human being in the course of a real case, but with training data at this point in time. And then we actually do end-to-end joint training of the model and the query policy. Should I ask the human or not? And then get their answer and then continue. Now, when we do this, we have to consider the cost of asking and put the cost into the equation, because in real time, this will once in a while be asking people for help, but we should be able to do that with the utility function. So we've been impressed by the results. To give you a sense for how things work, we found originally that 70% of human errors were in a region, using that tool I mentioned before to find regions of error, were in a region of the problem-solving space with the slides, containing just 10% of the cases. The standard machine learning approach without human input was failing in that region 30% of the time. When we do the joint optimization with machine learning, the system now becomes expert. It's forced to become expert in the region where people are weak. When they're asked, they don't help very much. So it puts more effort into that region, goes to a 0 error rate in that region, but it's kind of like a soft balloon. When you push the optimization, other errors pop up in other areas, but the system pushed the pop-up of new errors into problems that are easy for people to handle, building a better complementary system. So the last topic I want to talk a little bit about is coordinating initiative. And this is the idea of it's not all one shot ML, like perceive, act, perceive, recommend, act. Perceive, inference, explain, human acts. But there's in many cases, we have a volley, or we want designs for a mix of initiatives over time with humans and machines working together. It's a really challenging and important area. Just as an example from, I would say, outside AI, but not exactly, because an autopilot is a type of artificial intelligence from anyone's point of view. This is the China Airlines 006 case in February 1995. It was very salient when this happened, when I recalled this happening. But an analysis showed that with the 747 heading from Taipei to LA, the autopilot was in place when engine number 4, I believe, failed. And the system automatically came up with its solution to that situation in autopilot, but the plane began to process a bit. And at some point in time, the pilot turned off the autopilot. Now, there was a catastrophic transition to the pilot's control of the plane from the autopilot solution that led to confusion. And the 747 dove 10,000 feet in 20 seconds, hitting passengers experiencing 5Gs. And I think it's probably the only case where a 747 was confirmed as going supersonic. It recovered over the water with its wings bent, landed at SFO in an emergency landing. And I believe that plane is back in flight these days, I've heard, after repairs. But think about the issue of the mastering the mix of initiatives. Systems need to have a model of the human goals and understanding capabilities. There needs to be a transparency of state and intention between humans and machines. There needs to be common ground maintained. Initiative needs to be timed properly, and there needs to be critical decisions that are insightful about the passing of the baton between human and machine. Coordinating initiative is getting to be in the minds of the average consumer now. Tesla drivers will be familiar right away when they try out their autopilot about how Tesla handles confidence lowering in the ability of autopilot. The system will just scream at the user with a loud alert and say, auto steer is no longer steering. Confidently take over, and it throws control to the user no matter what they're prepared for. Of course, Tesla says always be prepared. The new approaches to the autopilot even have all sorts of signaling that needs to be done when it comes to traffic lights and to go, no go. Lots of overhead in thinking about the mix of initiative and its control. If you think about this more broadly as a direction for AI, think about a human and an AI system looking at a problem together, this blue blob. With a fluid general approach to coordinating initiative, you can imagine someday a machine saying, I see problems alpha and beta, and I can decompose that big problem into these two sub-problems. I can solve beta, but I can't touch alpha. Can you take care of that? And communicating who's going to solve what and recursing on this as a problem is solved over time. Just waiting for StreamYard to catch up with me here, because the animations are holding it up. Maybe it's a second here. Let me move on to the next slide. There we go. So there's been some interesting exploration of this area of work with mixed initiative in robotic surgery, based in Johns Hopkins and elsewhere. In one approach, and I'll show you some examples here. Some basic ideas are being used. Let's see if this video will display in this interface. To second here. Speaking of human computer collaboration, I'm learning about the ability of this system that we're sharing today to display slides to keep up with my animations and to display video. Let's try that again. Here we go. So this is an example, a snippet of video. This was on the front page of Science Translational Medicine just a few years ago, of work between Johns Hopkins and the Children's Hospital in Washington, D.C., of a robotic system working with a surgeon on a complex repair of an anastomosis, which is one of the more complicated surgeries in medicine. Using computer vision to understand the situation in terms of the tissue, and also with some reasoning going on about physician intention to suture jointly in this complicated scenario. At Microsoft, we built various kinds of virtual assistants of various kinds that call multiple components, multiple AI components, from learning and reasoning, perceiving, decision-making. And these systems have been used and fielded in areas, for example, like team coordination, like you see going on here. Front and back, you can see the system reasoning. And what you see here in the graphs are sort of some of the reasoning going on by the system as to the trade-offs and cost benefits of when to jump in to a complex conversation. And getting this right really changes things in terms of the fluidity of what I would call the general collaboration. Here it was with voice on a topic of collaboration, on a challenge game that was being played, but this could be done in physical space, in information space, or combinations. And I'll just end with one more video and give you a sense, I think, on a futuristic note, if I can get past this video. There we go. And this is on natural signals to ground for grounding joint collaboration and initiative between humans and machines. Was just a simple example we did with a team a few years back. We had built a system of the kind you saw with an agent that would be a receptionist, a virtual receptionist by my door at Microsoft. And the system has several services running: perception, understanding, detecting a healthy flow of conversation, answering a question domain level at hand. And in the past, we had all these interesting distributions, entropy measures for how each channel was doing. And we decided in some interesting work, I thought, to say, what would it be like to control the facial expressions and gestures of a virtual agent to capture all these dimensions. Now let's see if we can get audio to flow here and the video to flow, but this is kind of in some ways a nicer a view of all those entropy distributions than looking at them, in a display of the math and output. Let's see if you can hear this. This is the receptionist by my door.
Are you here for the 2 o'clock meeting with that? Sorry, did you say you were here for the 2 o'clock meeting with that?
Yes.
Is one of you John?
Yes.
Sorry, I can't tell who is speaking when you stand so close together. Which one of you said they're John?
I did.
Right. Hi John, that is expecting you. Will you be joining the meeting? Sorry, will you be joining the meeting?
Yes.
All right, I'd let Zach know you'll be joining his meeting with John. I'm sorry. I think Zach is running a little bit late. I'm pretty sure he's on his way. Just to be safe, I'll send him a note to let him know that you're here. Feel free to have a seat while you wait for him. Guess I'll see you later then. Bye-bye.
So if the fluidity of that video was as bad as what I saw on my screen, it kind of breaks the fluidity of the computation, trying its best to work with the timing and the gestures, eyebrows raised. They can't see. I can't see. Can you stand closer together? But that's just an example of how we can use core probabilistic reasoning and decision theory on top of the probabilistic reasoning to deal with perception and reasoning and set up joint collaborative experiences. So with that, let me end saying I touched on the commission report. You can read it at nscai.gov. I touched on a little bit of the report in terms of the engineering and performance issues, and then focused on toward augmenting human capabilities. And I touched at the end on some topics in mastering a mix of initiatives, which I think will be a quick direction for human AI teaming and for trust among humans and AI systems they're working with. So with that, I'll stop and take some questions.
Thanks, Eric. That was really great. And you reminded me that getting you a NASA fellowship when I was at Ames was one of the best investments we ever made at Ames in the future of AI. So
I loved it. I love hanging out at Ames.
Oh yeah. Well, and even getting to visit Mission Control is always a lot of fun. So a couple of questions. One was, one of the things that I've always enjoyed about this field since I've been involved in the human machine trust area, which I think entices you also, is the inherently interdisciplinary nature of the work. In fact, at that last review we had of the Air Force Office of Scientific Research Program, I believe we counted 12 different scientific disciplines ranging from computer science to cognitive science to experimental psychology to philosophy, and 9 different countries represented because of the inherently cultural aspects of trust. So one thing I'm wondering, one of the things that came up that I always thought was very interesting pointed out to us by the psychologist, was that human beings seem to make a transition between thinking of their agents, whether it's a dog or a bomb disposing robot, a transition from it being a tool to it being a partner. So I was wondering, did the commission consider the distinction between trustworthiness of AI systems as tools and the different issues of mutual trust between humans and machines when those machines are considered partners?
Yeah, I mean, I would say I hear your point, and it's a good one. there wasn't a focus on that in particular, but the issue of starting first with trustworthiness, robustness, accuracy, clarity on failures, transparency of inference, rationale and support for inferential recommendations was primary. Getting that foundation right was a focus. Now, in calling out human AI teaming and interaction and collaboration as a separate research area, there's quite a bit written about the scope of what that means. And of course, that covers the human AI psychology of trust. You could imagine, per what you were saying, Peter, that people can have unreasonable trust of AI systems. And there's a whole notion of automation bias that comes up. It's a big concern for systems that are working with people that people begin to rely upon. And when they're overseeing an AI system, especially when it's taking repeated actions over time, and it's costly to check everything it's doing. So I think it's just that your comment frames a nice direction of research, which actually would be in part largely, you say, well, let's say largely, but in part, but large area of study on trust between agents and how that could be used genuinely or abused, or how people might be biased one way or the other, and that could be a problem in systems.
So related to that was another question from the audience about AI applications needing to, if they're going to be considered partners, need to signal to the human partners their competency and their deficiencies. And in fact, when you think of human teams, sometimes, you add a new member to your team and you ask them what they're good at, and you might believe it. You might look at their credentials, or you might observe them in the field to determine their competencies and deficiencies. So the question was, what advancements do you have being made to enable both the machine agent knowing its competencies and deficiencies, in other words, self-monitoring, self-understanding, and signaling that to its human teammates?
Well, that's a really rich and growing area of work. It's good to use a Rumsfeldian concept during a DoD talk to DoD audience, and that is we've done work on unknown unknowns, how systems can be probed for the unknown unknowns in their area, how they can work with humans to help them figure that out themselves when working in the open world. That's a really interesting direction of work. How does a system find its own blind spots through its own studies, as well as working with people to find regions of blind spots? Secondly, that area I mentioned on error analysis, putting that richly into context-sensitive, real-world execution, I think it's going to be really useful. People feel a lot better in a situation as the sun glares into the lens of whatever is being used to perceive, let's say, a scene, to get a direct feed on what this means for all the test sets on that specific situation, time of day, location, and so on. Even understanding whether a system has been certified for a certain sub-context, like in this use with this background. We know that we have challenges not talked about enough with transfer learning. There's an idea that you build a model and use it everywhere. If it's not the right kind of model with narrow scope, you have trouble tuning it and parameterizing it for the situation you're in at the moment. So we're requiring that kind of self-test and working with people to assure that you're not using a model that people were confident in somewhere else is going to be critical. So I think there's multiple directions in this space. Models and systems that are built in subsystems that probe for blind spots. It's a really active, we're not investing enough in that space. It's an important area of AI in the open world. Secondly, really sort of give people a sense for representative performance in a situation that really is matched to the current situation and in real time. And if there's uncertainty about that, making sure that the end user knows that so they can't depend on that kind of self-knowledge. So I think this is just, you bring it, let's just freeze that question and say this needs to frame multiple and deep investments in AI in the open world.
Well, thank you, Eric. And thank you again on behalf of everyone who put this program together and the U.S. Air Force and the federal government as a whole, and who knows what else, for spending the time today with a really fascinating talk about the work.